All right, thank you, everybody. So we are resuming with a talk by Joel Lewis, who will tell us about combinatorial formulas for shifted dual stable Grothendieck polynomials. So after that, we will have a break before the last two talks of our session. So thank you, Joel, and let's begin.
Yeah, thanks, Zach. So quick outline of the talk. So like Anna said, people like Schur polynomials because they like tableau combinatorics. So I'll just sort of briefly remind you of things that she just told you better, and then I'll talk about some variations of Schur polynomials, Grothendieck polynomials, and the Schur P and Q polynomials, and then our results at the end sort of are like what happens if you do both of these generalizations of Schur polynomial variations of Schur polynomials at the same time. So just for all right. So whatever. Over the integers. Everything in this talk is over the integers. Or sometimes there will be this parameter beta that is it's just for making things homogeneous. So maybe over the integers with beta. Really, my only complaint about Anna's talk is she draws her tableau upside down. So I'm going to be in French notation. Yeah, I'm gonna like say words from geometry. So that's for those of you who know what those words mean. I'm not one of you, but hopefully it'll be all right. So Schur functions. I guess I should say that another difference between our talks is that all of my symmetric functions have infinitely many variables always. So sim is like symmetric functions in infinitely many variables, and the Schur polynomials are a basis, and they're a wonderful special basis. And you can define them lots of different ways, and like here are a couple of ways you can define them. They are the unique basis that satisfies this Cauchy identity. Like you can't put any other basis here. Well, okay, you can change their signs and you can reorder them, but as long as you're over the integers, it's the only basis that this satisfies this Cauchy identity, which is the same thing as saying it's the unique orthonormal basis under the Hall inner product. Or you could define them combinatorially as generating functions for tableau, or you could define them in terms of geometry as coming from Schubert classes in the I have to read this in the cohomology ring of the Grassmannian, and there are like lots of other ways that you could define them also, which I'm not going to talk about. So I want to think of this as like my package of interesting things for the purpose of this talk that about the Schur polynomials is Cauchy identity, combinatorics, and geometry. So you could change the definitions and get other Schur-like things. So like if you like the geometry, you could do K-theory instead of cohomology, or like you could do other Grassmannians instead of the normal complex Grassmannian. Or if you like combinatorics, instead of doing semi-standard Young tableau, you could do one of many other different kinds of tableau, which I'll sort of mention later. And what's sort of surprising and wonderful is that these things like often go together. So if you find a family of tableau with an appropriate weight function so that the generating function is symmetric, there is often also a geometric thing for which these are the representatives of an appropriate class. So like, I don't know, here's one example that the Schur Q functions, they're also cohomology representatives in the orthogonal Grassmannians, and there's some representation theoretic thing, and they're these like shifted mark diagrams all at the same time. So you tend to get these things coming together, which is great. The thing that you lose is that the Schur functions are the unique self-dual basis in this sense. So you can't change them and still have a self-dual basis anymore. But what that means is so you lose this wonderful self-duality, but then you just get more objects. So like you lose a property, but you get more objects because there's still a dual something, right? There's some other basis of some other Hopf algebra of symmetric function-like things for whatever your favorite basis is that you can put next to it that will give you a Cauchy identity of some sort. So you get some dual basis for each of your bases. All right, let me give you a concrete example. So Grothendieck polynomials. So these come from K-theory, as Anna mentioned. Combinatorially, they are the stable Grothendieck polynomials. They're generating functions for set-valued tableau. So this is just like semi-standard tableau, but you can put multiple entries in the same box, and it still has to be weakly increasing along rows and strictly increasing up columns. And then you see like beta shows up when you have like too many entries in your tableau. Beta just sort of like keeps track of that. So it's a homogeny. You should like think of it in this case as having degree -1 so that the whole thing is homogeneous. But it's just there as bookkeeping device really. In particular though, when you set beta equal to 0, you get back Schur's because it kills all the ones that have extra entries. That's when you get the beta. So all right, so they come from this nice combinatorial thing, and then you can define dual stable Grothendieck polynomials via the Cauchy identity. They are the thing that you put next to the stable Grothendieck polynomials to get this Cauchy identity, and they also have a nice combinatorial formula. Instead of being in terms of set value tableau, they are in terms of reverse plane partitions. So now you're weakly increasing in both rows and columns, but you change the way you record the weight. So like if you happen to violate the semi-standard condition going up a column, that like doesn't give you new contributions to your weight. So like here you can put in 3 ones, but you only count x1 squared because you count it by like the number of columns that have ones in them. And then like now beta is again doing this homogeneity thing so now you should think of it on the dual side as having degree 1 instead of degree -1. So you get reverse plane partitions, and then you can like get even more symmetric functions because like for the Schur's there's this involution omega that was mentioned in Jonah's talk this morning, that you know it sends S lambda to S lambda transpose. Okay, so it's just permuting your basis. But now on these it might do something interesting. And so okay, on the stable Grothendieck's it just does a change of variables, so it's not that interesting. But on the dual stable Grothendieck's you get this new family of things, the conjugate dual stable Grothendieck's. That are, again, combinatorial generating functions for something. Now, all right, so Thomas and Pasha aren't here, right? So they called these tableaux like valued set tableau. The idea is they're like dual to set valued tableau. So it's like this very cute bit of wordplay that's like incomprehensible. It's a terrible name. Don't use it. Call them. Yeah, just call them bar tableau because that's what you get, right? You like each entry can like spread itself over several boxes, but it's still semi-standard, so they just make these like bars. This is a much better name. You should call them bar tableau. All right, so they're generating functions for bar tableau. Okay, so and again, if you put beta equals 0, you get back S lambda. Okay, so that's like one variation on Schur polynomials. Yeah, because this is wrong. That's why. Because I copy pasted something and didn't fix it. Yeah, this should really be x1, x2. Thank you. Yeah. Okay, so totally different variation on Schur functions. You can take shifted diagrams. So like one way to think about a shifted diagram is just like instead of being left aligned, you're now like aligned to the line y equals x. Another way to think about it is you've taken a self-conjugate shape and you've like folded it in half. And as a result of that folding, you sort of have 2 copies of the variables. So you have sort of one copy that remembers that it came from the top half before you folded, and you have one copy that remembers that it came from the bottom half before you folded. So you have okay, marked alphabet here. And so like the unmarked ones behave normally. They weakly increase in rows and strictly increase in columns, but the marked ones have been like folded, so it's like reversed, so they weakly increase in columns. So you can put like a 2' above a 2', but you can't put a 2' next to a 2'. They strictly increase in rows. And so the Schur Q function is the generating function for these things. And it turns out to be symmetric. And if you can ask, like, why would you do the marking? And one answer is, well, because if you don't get a symmetric function. So the whole thing's off. So that's Schur Qs. And Schur Ps are very, very similar. You just like aren't allowed to put the primed entries on the diagonal. And in fact, that means that the Schur Ps and the Schur Qs are like very closely related to each other, because these conditions, you can always prime or unprime the diagonal entries sort of freely. So the Schur Ps are just a power of 2 off from the Schur Qs. And like if we were over a field, this would like not deserve another name. But if you're over the integers, this is like an actually important difference, right? They generate a different sub-algebra over the integers than the Qs do. So you really should think of them as different in this context. And they together satisfy a Cauchy identity, which for reasons it's a little bit different looking, the product here. I don't know, but that's what it is. So they are the sort of dual bases to each other. So that's this sort of other variation of Schur polynomials, are these shifted guys. Okay, so Schur, Grothendieck, shifted. All right, so now we're gonna do both of these variations at the same time. So why are we gonna do this? Well, we're gonna do it because Ikeda and Narusa were studying the K-theory ring of coherent sheaves on Lagrangian Grassmannian. All right, and it turns out that there are these representatives for the Schubert classes in whatever that is, that are these K-theoretic Schur Q functions, and they proved that these functions this is like literally just you take the two variations at the same time. So you're in a shifted diagram, you have a marked alphabet, you can put multiple entries in a box. The unmarked entries weakly increase in rows and strictly increase in columns, and the marked ones do that backwards. And then you have beta again is just degree -1, making it all homogeneous. And so these are the generating functions, and the GPs are the same thing, but you aren't allowed to put primed entries on the diagonal. But actually this is different now, because you can't just like randomly prime and unprime diagonal things totally willy-nilly, because you might be in this situation where say like 3' and 3 are together in a box, and you can't unprime that 3' because then you can, right, because it's a set. It's not multi-set valued. So it's not true anymore that the GPs are just a power of 2 times the GQs, although that does happen at the lowest degree when you set beta equals 0, because when you set beta equals 0, you get back just the regular Schur P and Q functions. Okay, so shifted, marked, set valued tableau, and now you can ask about the dual ones. And so Nakagawa and Narusa defined the dual K-theoretic Schur P and Q functions. And the way they define them is they wrote down a Cauchy identity. It's a little more complicated. The thing about this more complicated thing is you should just like check when you put in beta equals 0, it becomes just the shifted version again. So it's like more complicated, but at beta equals 0, it's the same. You have 2 versions because you have a QP version and a PQ version. And so they defined these things, and they conjectured formulas for them as generating functions for shifted, marked, reversed plane partitions. And then Chu and Marburg conjectured, all right, for the conjugate ones, formulas for shifted, marked bar tableau. And our theorem is those conjectures are correct. So, okay, let me tell you what the conjectures actually are. So G little gq, so this is a dual K-theoretic Schur Q function. They are generating functions for shifted, marked, reversed plane partitions, which are, okay, the object is a reverse plane partition on this doubled alphabet. And now, like, the weight here is like the unprimed entries count. You count how many columns they're in. The primed entries, you count how many rows they're in because they've been folded. And then the GP version is like something with a diagonal condition also. So that's the GPs and GQs. And then the conjugate ones are shifted marked bar tableau. So again, each entry can now spread itself out among several boxes while otherwise obeying the conditions of the shifted marked tableau. Yeah, well, so now, right, so the unmarked entries are allowed to be next to each other in rows, so they can make horizontal bars, whereas the marked entries can be next to each other in columns, so they can make vertical ones. So yeah, you now have a mix of horizontal unmarked bars or unprimed bars and vertical primed bars in the same shape. And again, some diagonal condition for the P version. Okay, so that's the theorem. A few words about how you prove something like this. One thing that I haven't been saying all through the talk, sorry, Eric, is that the thing about these combinatorial formulas is it's like completely unclear that any of them define a symmetric function, right? I mean, you can say like, take the generating function, and sure, that's a thing, but it's like completely not obvious a priori that it's symmetric in the variables. And so in each case, the way you prove that is with some sort of weight reversing involutions, these Bender-Knuth involutions that allow you to move around the fillings to count the degrees to see that the monomial for one permuted thing is the same as if you rearrange it by doing a series of involutions. So that's, whereas by contrast, the definition as the thing that satisfies a certain Cauchy identity, those are sort of just obviously a priori symmetric because the right-hand side is symmetric, and so you extract a coefficient, and it's just sort of for free. So like the first thing you need to do is you need to show that your combinatorial thing is actually a symmetric thing, so you need a Bender-Knuth involution. And the idea of our Bender-Knuth involution is like pretty straightforward. It has a few moving parts. This is just one of the parts. But like here, if you have, for example, some horizontal rows of 1s and 2s, what you can do is you can like look for the places where one bar of 1s ends and another bar begins, and like you just move that into the 2s in the same column, and vice versa. And so this is a sort of local weight reversing move that you can do. It behaves very nicely. You have some other moves like this. You have to do stuff with the marked entries and the unmarked entries also. And the problem is that at the diagonal, everything is terrible. And so like the ideas of this proof are pretty simple, and the proof is 10 pages long. It's just a real hassle. But that's what you do. And then once you have that they are actually symmetric functions, then you go by induction. You basically prove, you can explicitly compute for one row shapes what the polynomials are on both sides, and then you do Pierre rules, which sort of requires you to be working all the time with skew shapes. So if you're like worried that there weren't enough adjectives on Tableau in this talk, you can make everything skew also. And so then you have a Pierre not and you know that it's true for one part things, and that is what you need to do it by induction, which again is like, it's not, whatever, it takes a while to write out the details, but the idea is not so bad. Okay, one last thing is like, what is there anything you can do with this? One thing is that these K-theoretic guys, they have arbitrarily high degree, right? Like your sets can be as big as you want. So if you just ignore the betas, like you can have in the x degrees, it can be arbitrarily large, and that means that when you multiply two of them, it's completely not clear that it's a finite linear combination of them. Or equivalently, it's like not clear that the linear span of these things is a ring. Like you might have to take a completion or something. But Ikeda and Narusa conjectured that they are rings. In the case of the capital GPs, this was done by Clifford, Thomas, and Young, who gave a good answer in that they gave an explicit Littlewood-Richardson rule for multiplying these things. When you combine our work with the work of Chu and Marburg, it does imply the other half, so that the GQs also generate a ring. However, it's not as good an answer because it doesn't give you a concrete Littlewood-Richardson rule. So if that is interesting to you, you should read Eric's paper, not my paper, more recent, that gives a sort of comprehensive account of all of these objects and what of the natural questions about them, like which ones have known Littlewood-Richardson rules and so on, are still open. Yeah, thanks very much.
We have time for a few questions.
So are there RSK-like algorithms to prove the Cauchy identity?
The question is, are there RSK-like algorithms to prove the Cauchy identity? Are there for any of these objects other than?
There's candidates but no proofs.
Yeah, okay, so there are candidates but no proofs. By the way, this is going to be a recurring theme that I'm going to ask these two guys for the answers to any questions you might have. So not like the usual sure case. There are not these nice RSK proofs of the Cauchy identities.
Yeah, so at the very end you were talking about, I think you said there was an explicit comment for the Littlewood-Richardson rule for the GPs, but you said not for the DQs. Do you happen to have some loose sense of what the obstacle is or obstacles are for finding such a thing for the GQs, just like in your work on it?
Yeah, so the question is do I have a sense of what the obstacle is to having a Littlewood-Richardson rule for the GQs in comparison with the GPs? Eric?
Yeah, I don't have there's some geometry, but also just more complicated.
Yeah, all right. Eric says maybe there's some geometric reason, but it's just more complicated. Yeah. Required to have is that right? For the little GQ? Little. Yeah, okay. Yeah. Yeah.
Do these more general semantic functions also have determinantal formulas like the Combinatorial type?
Yeah, okay, yes. Yes, there are Jacobi, this is not a joke, all right. There are apparently Jacobi-Trudy type ident for all of them?
I think for the GQs have better behavior.
All right, for the GQs at least, maybe not for all of them. Yeah, Bruce?
Do you know any relations satisfied by the Bender-Newton relations?
Do I know any relations satisfied by the Bender-Knuth involutions? No, they're really, like some parts of them are easy to understand, but when you put it all together, they're like a horrible mess. It's something we could experiment with, but did you ever check anything like that? Yeah, I think we were just happy to prove that they worked. That was exhausting enough.
I think one has to say that the Bender-Knuth evolution does not satisfy nice relations. It was Lascaux and Fitz-Berger who modified them so that they satisfy the great relations.
Can you say that again?
The Bender-Knuth evolution does not satisfy.
Oh, just the normal Bender-Knuth
That's
involution.
the normal Bender-Knuth
Okay, it doesn't satisfy nice.
relations.
doesn't satisfy nice relations.
Machine modified this
Okay.
with the goal of having the break relation.
Okay. It's really great to have an audience full of smart people who know things. Yeah.
Does it make sense to have tuples that are both set valued and barred?
Both set valued and barred. I mean, you could write down a definition. As far as I know, there is, I do not know either whether you can choose a natural weight function to make a generating function for such things symmetric, or whether, if so, there's any geometric object associated with them. It's a sort of thing that would be like, you could write down a definition and experiment, and if it were symmetric, that would be very interesting, I think, and then you could like try to figure out what could it correspond to, but I don't know if anyone has ever done that. Should I stop at some point?
Yeah, I think in the interest of time, if you have more questions, you should come up and talk to Joel. Let's thank
No,
him.
talk to Eric.